Hello, everyone. Myself, Professor Satish Patil, Assistant Professor from Mechanical Engineering Department, MIT School of Engineering, MIT Art, Design, and Technology University, Pune. Today, we are going to conduct the experiment on gyroscope. The title of the experiment is to verify gyroscopic principle. The learning objective of this experiment happens to be we are going to understand what is gyroscopic effect and how are we going to analyze gyroscopic effect. Okay? So we will move for the experimental setup which is available for this experiment, wherein we will learn what all detailed specifications of this setup are. Okay? So we come to the specifications wherein we will be understanding to know that the major component for the gyroscopic experiment to understand is disc, which is made up of stainless steel, heavy disc, which has got mass of 5.7 kg, and the dimensions of the disc are diameter around 300 mm and thickness of the disc is 10 millimeter. Okay. With this, we also have variable speed motor with speed controller. So in this experimental setup, the variable speed motor is here, and with speed controller, which is located here. On this speed controller, we can see a display to measure how much RPM the disc is rotating. Okay. And that RPM will be taken through the sensor, tachometer, which will measure at what RPM the disc is rotating. Okay. This speed of the motor will be controlled with the help of this variable dimostat, where we will be controlling the speed of motor in line speed of disc. Okay. Now coming to the actual focused area for this setup, which is this gimbal. We need to understand how this gimbal is going to work. Then only we will understand the gyroscopic effect in detail and the measurement of its values, gyroscopic torque. Okay. So for this, the disc which is allowed to rotate in horizontal plane, the horizontal plane can be considered in this direction. Okay. Now, the disc is also allowed to rotate perpendicular to this horizontal direction in this way. So let us say disc is rotating in this horizontal direction. Okay. There is one more position changing of the disc, that is in this direction. So this gimbal is allowed to change its position about this horizontal axis, which is perpendicular to this axis. Okay. At the same time, the disc is also allowed to rotate about vertical axis. That means there are three mutually perpendicular axes about which the disc is going to change its position. And that's a necessity of understanding gyroscopic effect. Okay. Now, if you look at this, whole arrangement is made such that the disc is allowed to rotate about three mutually perpendicular axes, and at the down portion of this gimbal, we have blue pointer. Now this blue pointer is used to measure at what angle the disc is going to change its position. That angle we can measure, we can identify with the use of this pointer. So we have at the bottom surface of the gimbal, we have angular scale, okay, wherein we are able to measure how much degree this disc is going to change its position. With the help of this pointer, we are able to get into that. So this is how the construction of the gimbal is. This will allow us to understand gyroscopic effect and to measure gyroscopic torque. Okay. Now, how are we going to perform this experiment? it has got two ways to perform this experiment. Okay. How? In first case, we are going to vary speed of the disk, and we will be using the one mass which is available at our hand out of these three: half kg, 1 kg, and 2 kg. Now, if we are setting up speed for the disk with the speed controller, we can take the one case. Whereas a second case is we will be keeping speed of the disk constant, and we will be using these three masses, and then we are observing what would be the effect of gyroscopic couple. Okay. Shall we perform? Yes, we will go ahead. So I'll just introduce our lab assistant, Mr. Mahesh. He will assist us in this experimentation. Okay. So Mahesh sir, will you please set up the disk speed at one position? Yes. Let us say we are going for first case where we are going to vary speed keeping mass constant. So for this case, let us say I will take a mass of 1 kg, and we are going to vary the speed of the disk. For the first case, first sub case, let us keep it the speed as it is here, let us say around 770 RPM. Okay. With this RPM, we just need to understand that right now axis of spin of the disk in this direction, we will make use of a right hand to just denote where would be the axis of position, axis of spin position. In that case, if I use these fingers in the direction of rotation of the disk, where from observer side, as it is rotating anti-clockwise sense, so I will use the fingers in anti-clockwise sense. The thumb of the right hand will indicate position of the axis of spin. So this is axis of spin. We will just ensure that to get in the stabilized position where the axis of spin remains in horizontal position. Now we need to understand one more thing. According to the construction of this gimbal, we have counterweight here where we are going to put the mass of 1 kg. Okay. Now this counterweight is going to balance the motor on the other side of the disk. So which will ensure before keeping this mass, the axis of spin remains in horizontal position. Okay. So once we ensure that it is in horizontal position, we will try to keep this mass on this platform. At the same time, we need to know that at how much distance we are keeping this 1 kg mass. Okay? And that distance, as per the specifications of this experimental setup, it is from the mid plane of the disk, we need to measure it till the line of action of force of the mass. And that happens to be 200 millimeter in this case. So let us go for keeping mass exactly. Now, before keeping mass, what we need to observe? As a result of the gyroscopic effect, how it is going to behave. So that I will explain first, and then I will keep this mask on the platform. Okay. What we have to observe, first thing, as soon as I keep mass, I am going for getting force in this direction, downward direction. That means the axis of position which is in this direction is going to change its position downward. That means this motion of the axis of spin is nothing but axis of precession. So this axis of spin is going to precess in this direction. It is changing its position about this axis, horizontal axis. The axis of spin is going to change its position about this horizontal axis. And effect of gyroscopic torque will be about vertical axis. That's a third axis, which is mutually perpendicular to both of this. That is axis of spin and axis of precession. Okay. So we need to observe, if I keep this mass and the line of action of force is getting this axis of spin downward, then whether we are getting any moment of axis of spin about vertical axis or not. That is what we are going to observe. Okay. So let us observe, and for the measurement of gyroscopic torque, what are we going to observe? That if at all, if I keep mass here and it is going downward, if at all this axis of spin while going downward, if it changes its position about vertical axis, then it must go on this side or this side. Okay. So whatever travel of position of this axis of spin, either on this side or on this side, needs to be measured with the help of this pointer. Okay. And that will be measured with this stopwatch. So how are we going to measure that? With the making use of this angular scale, we will fix up for, let us say, from this position, it changes its position for 30 degree. Okay. So how much time we require for changing from 0 to 30 degree? That is what we will measure with this stopwatch. Okay. So let us go for it, and then how are we going to measure the gyroscopic torque? We will discuss after that. Okay. So let us start. This is the 1 kg mass. You just observe right now the disc is stable with horizontal axis, axis of spin in horizontal plane. I will just keep smoothly without disturbing its stability. For that, as soon as I leave this, there must be some change in the angular position. So there you can find the change in angular position. So we need to measure time required for that change in angular position. Okay. Let us go for once again and measure time. Okay. This is what the observation we have done. So what did you observe? As soon as I keep mass, the axis of spin is going downward as well as it is moving towards this direction. And that time we need to measure. So there is gyroscopic effect which we observe. Let us analyze that gyroscopic effect once we measure time required for the 30 degree angle. Okay. So I'll just put the stopwatch on the 0 reading, and slowly I'll keep this mass. Okay. So the time required for changing its position from 0 degree to 30 degree happens to be around 1.84 seconds. Okay. So for this case, the angle considered to change in its position is 30 degree, and the time required for that is 1.84 seconds. So how are we going to make use of this? How are we going to make use of these measurements? So for that, we need to understand the axis of spin, where we will get to know what is angular velocity of the disk. Okay. With the help of this RPM reading, we are in a position to calculate angular velocity of the disk. That is omega. Next, this axis of spin is changing in this direction because of the mass kept on the platform. So that is precession, and angular velocity of precession we can calculate with the help of the angle measured and time required for that. So d theta by dt is the equation which we will use to measure angular velocity of the precession. So we have omega with us, angular velocity of the disk. We have omega p with us, that is angular velocity of the precession. which is d theta by dt. So we know angle, we know time required for that. So just we need to ensure that angle to be taken into radians. Okay. So 30 degree you can easily convert it into the radians, and then we can get angular velocity for the precession, that is d theta by dt. In that case, we also need the moment of inertia of the disk. And for that, you have already mass, you have already radius of the disk, with which we can calculate what is moment of inertia of the disk. So gyroscopic torque can be calculated with the use of moment of inertia, omega, and omega p. Okay, so that is I, omega, and omega p. If we consider product of these three quantities, then we will be in a position to find out what is gyroscopic torque. Now this measured or calculated gyroscopic torque needs to be verified with applied torque. Now how I am going to measure applied torque? That is as simple as that. We used 1 kg of the mask and we kept it on this platform. That means we are using mass which is moving downward, which is 200 millimeter away from mid plane of the disk. So we know what amount of force getting down. We know at what distance it is acting from the mid plane of the disk. So we can easily find out what exactly is applied torque. So we know applied torque, we know measured or calculated gyroscopic torque. We will compare these two and we will just find out what is percentage error between these two. Theoretically speaking, these two torque, calculated gyroscopic torque and applied torque, needs to be same. But with the experimentation done, with the readings taken, we will verify it, the percentage error, whether it is nearer to 0 or not. And we'll definitely come to know that these two torques are similar, same in magnitude, and they will be giving us percentage error which will be close to 0. Okay. This is how the verification of gyroscopic torque will be done with the help of this experiment. Okay. That's where we come to the end of case number 1. Okay. Thank you. We will get ahead with case number 2 also. So we came to know that we will get percentage error which will be close to 0, isn't it? After calculation of measured gyroscopic torque and applied gyroscopic torque. Now the same set of procedure we need to do it or repeat it for different speeds. Right now we have done it for, let us say, the speed around 770 or 780. Now we can make it for the different speed. That is, let us say I'll increase speed little bit and we'll get to know that it is around 900 or 1000 RPM. The same set of readings, we will repeat it twice or thrice, and the case 1 can be justified with percentage error which is close to 0. Okay. Next, we will move for case number 2. Hello again, friends. Now we will discuss case number 2 on this experiment where we are going to have the variation of mass and speed constant. So let us say we are going to repeat the same experiment for different masses, keeping constant speed. So Mr. Mahesh, can you please set the speed around, let's say, a little bit more than 1000 or maybe 1100 RPM? So you can observe the rotation of the disk. Okay, as we need to know what is the rotation, sense of rotation of the disk, and with this, with the use of right hand rule, we will put our fingers in that sense of rotation to know where is the axis of spin. Okay. Now, this case, we are going to change masses, right, from half kg to 1 kg to 2 kg. So we will be utilizing all these three masses for calculating three sub-cases of second case. Now, if I put the speed around 750 RPM, let us say, then I'll start with mass half kg. Now, as we know, gyroscopic effect would be similar to the earlier case because I am again putting mass here and the force which is acted vertically downward. So axis of spin is going to move downward. It's going to process downward. And at the same time, it is going to observe the gyroscopic effect that is on this side, which was same in the earlier case. The same thing we can observe here also. Just to take readings of how much time required to complete 30-degree rotation for half kg case. So slowly, without disturbing the setup, I'll put the mass, okay, and I can start the timer and I'll measure for 30 degree. For this case, we require 2.97 seconds. Time required for moving with the angle of 30 degree, 2.97 seconds. Okay. So for this particular speed, for this particular mass, we get time required for that to travel through 30-degree angle. In this case, we will be understanding that if I'm using the different masses, I will get different time for travel through 30 degree. So these are the three sub-cases which we can make use of under the case number 2 with constant speed and mass variation. The first mass half kg, second mass 1 kg, and the third sub-case would be for 2 kg. So this is how we can repeat the steps, measure the time required in every case, and calculate measured gyroscopic torque and compare it with applied torque to find out what is percentage error. Theoretically, the percentage error should be 0, whereas practically we may get some value, but that value should be closer to 0. That is the case. Now, understanding effect. I'll just explain detailed effect understanding where we have three mutually perpendicular axes of spin in this case because it is rotating anti-clockwise sense, and axis of spin is here. So we have this axis of spin, we have this is second axis perpendicular to the axis of spin, third axis perpendicular to the both of these. Okay. So these three mutually perpendicular axes, we are going to make use of understanding how the gyroscopic effect would be. So that, for understanding that, the rotation of the disk and axis of spin is changing its position. So how it is going to change its position if I push this axis of spin downward, why it is going on this side? We need to understand it with the use of right hand rule itself. And what is that right hand rule? Let us discuss on that, which we have discussed it already in a theory class. I'll repeat it again here. So what we have, the axis of spin going downward. So in same direction, you just change your right hand by 90 degree. So earlier it was in horizontal position. Now by 90 degree it is vertically downward. Okay. So precession is happening around this axis. Now this is the position of active gyroscopic couple. So vertically downward direction axis will give us finger positions which will change axis of spin which was earlier in horizontal direction to change on this side. But that is not axis of active gyroscopic couple. That is reactive gyroscopic couple, exactly opposite to this active gyroscopic couple. Now the axis of reactive gyroscopic couple would be vertically upward, where the fingers show that the moment of the axis of spin should be towards this direction, and that is what we are getting. If I have axis of spin which is pushed downward, but it is going on the left side simultaneously when it is moving downward. So that is what we observe. If I press, let us say gently I press this disc little bit downward direction. Okay, this is what we observe. So when I try to push it in moving to downward direction, it is moving on this side also. This is the effect of reactive gyroscopic couple. This is the one thing which we need to understand. To understand analysis of gyroscopic effect, we should be in a position to understand how the reactive gyroscopic couple would play in the gyroscopic effect. So I'll take another case to understand the right hand rule, use of right hand rule. How? Let us say I have this disc with stabilized axis of spin. Okay. So rotation, sense of rotation is anti-clockwise and axis of spin towards observer. Now I will just try to push this axis of spin on that side. Okay. Let us push gently the axis of spin towards this side, and we will observe where exactly the reactive gyroscopic couple is going to play. Okay. So gently push this. See, the reactive gyroscopic couple is taking axis of spin in upward direction. That means what? When I have the disc rotating in horizontal plane, okay, I'll repeat it again and observe that if axis of spin is in horizontal direction, and if I gently push, I'll repeat again, observe closely. As I repeat, the axis of spin position, instead of remaining it in horizontal direction and changing its position in horizontal plane itself, it is moving upward also. So that's what we need to observe. So this is how it happens. See, it is going upward, and this rear side is going downward. So that's what we need to observe. How are we going to justify this with right hand rule? So it is as simple as that. Making use of right hand rule, we have axis of spin here. I am trying to change its position towards this side, right? I am pushing in this direction. That means axis of spin is changing in this direction. So change this thumb exactly 90 degree. So it is still in horizontal plane and changed by 90 degree. So this is the position of active gyroscopic couple. And exactly opposite to that, towards me, this is a reactive gyroscopic couple. And what finger shows? The axis of spin should be moving towards upward direction. So that's why when I try to push this axis of spin in this way, it is also going upward, because the reactive gyroscopic couple is pushing the axis of spin in upward direction. Let us observe one more time. Okay. Whatever we discussed with the use of right hand rule, we will observe again, third time. So this is how I'll just push. See, this is the axis of spin, which is changing in this direction. So I'll change it by 90 degree, but it is going upward. So this is active gyroscopic couple, which should push downward, but we experience reactive gyroscopic couple, which will take this axis of spin to the upward direction. This is what we get gyroscopic effect on the rotating disk, rotating masses, which has got high moment of inertia. So this effect plays important role in understanding the behavior of rotating masses at higher speeds, highly weight rotating masses rotating at higher speeds, which we can say it in the case of turbines, it will be in the case of ships, aeroplanes, as we discussed it in theory class, as well as we may observe or we experience it in case of two-wheelers and four-wheelers also. Okay? That all analysis we learned already in the theory class. Just this is the practical wherein we verified the gyroscopic couple with its effect as well as its measurement and verifying it with the theoretical value, which is giving us the percentage error between measured value and applied value close to 0. Thank you. I hope you understood the experiment based on this verifying gyroscopic effect with the help of the setup which we have. Thank you. Thank you very much. If you have any queries, feel free to communicate me on my official mail ID, that is sateesh.patil@mituniversity.edu.in. Thank you very much.